Now, I want to introduce you now to the structure of ATP. In our previous session, we looked at how ATP is an energy currency in all the living organisms, and we gave the reasons for that. Now, I want us to look at the structure of ATP. Now, ATP is usually made up of ribose and adenine, which are joined together to form what we refer as adenosine. If you look at our image here, you can see adenine is joined with the ribose sugar here, which is a 5-carbon sugar. Adenine is actually a nitrogenous base. Is joined with ribose to form what we refer as adenosine. So this and this one, that is the adenine and the ribose, they make adenosine. Now, attached to the adenosine are 3 phosphate groups. So we have the first phosphate here, the second, and the third. My discussion will majorly look at the third phosphate group and during the synthesis and the synthesis and the breakdown of ATP. Now, these 3 phosphate groups are joined together using what we refer as the phosphor and hydride bonds, or what we refer as the phosphate bonds. That's the phosphor and hydride bonds highlighted here, and also we can refer them as the phosphate bonds. I advise you to go with the phosphate bonds. Now, if you look at this, it's just a basic structure of adenine, that's of ATP, whereby adenine joins with ribose and the 3 phosphate groups to form ATP. Now, how does ATP produce energy when hydrolyzed? I earlier mentioned in our first video, if you looked at, you happen to watch it, that for every hydrolysis of 1 mole of ATP, that 4 kilojoules of energy are released, meaning that when this last phosphate group is broken down, you see in our diagram here we have the 3 phosphate groups attached to form adenosine triphosphate, which is ATP. Now, when you add water, this is an hydrolysis reaction in the presence of ATPase. ATPase is the enzyme that catalyzes this reaction. It's an enzyme that catalyzes both the forward and the backward reaction. That's why you see it's indicated at the center here. Now, that ATP is when it undergoes hydrolysis in the presence of ATPase, the third phosphate group is broken. That's the bond that is broken, energy is released, and in this case I've said is that 4 kilojoules per mole of energy to form inorganic phosphate written as Pi and adenosine diphosphate, which is ADP. Now, some of the energy is lost in form of heat energy and it's wasted, as I've mentioned in my second point here, because you realize not all the energy in a reaction is conserved. Some is lost in form of heat and therefore it becomes as a waste, although some can be used to warm the bodies. Now, the rest of the energy that remains is used in various metabolic processes in the body that require energy. In the first video clip, I talked about muscle contraction, protein synthesis, active transport, and we talked about the light independent reactions where it is used in form of ATP from the light dependent reactions, and we also looked at how it is used in cell division. So those are some of the metabolic processes. Now, in my next slide, we are saying that it's just a continuation of what we did. We have already explained that the synthesis reaction is provided by the enzyme ATPase and it requires an energy input, which I've already mentioned, while the breakdown is a catabolic reaction, and in that case it releases energy. It does not require an energy input. Now, the energy that is required to synthesize ATP, it comes from what we refer as catabolic reactions or reduction oxidation reaction, what we refer as redox reactions. Now, what are catabolic reactions? Now, catabolic reactions from our AS Unit 1, we said that it is actually the cut or the breakdown. The word kata refers to breakdown. So when we talk about catabolic reactions, they involve the breakdown of bonds. Now, the opposite of catabolic is anabolic, which deals with synthesis. Now, the reduction and oxidation reactions, these ones, they deal with the movement of hydrogen ions or hydrogen atoms and electrons. Now, reduction is whereby organic compound, or let's say substances, gain, like in this case carbon dioxide, it gains hydrogen or electrons, and oxidation, they involve now the release of those electrons and hydrogen, and then those are what we refer as redox reactions. And you will realize that this one majorly they are facilitated by what we refer as hydrogen acceptors or electron carriers. Now, the synthesis of ATP, we say it is a condensation reaction, while the breakdown is hydrolysis, because this hydrolysis requires the addition of water, while the condensation reaction involves the release of water molecules. Now, our next part I want us to look at is the making of ATP through the electron transport chain. Now, the basic thing I want you to know here, not that it's basic, but the major thing I want you to know here is the electron transport chain and what it is. From the name itself, it shows that the electron transport chain, it deals with the transport of electrons, and it's a series of reactions, as you can see, because it's a chain. Now, we'll be referring as ETC because we can't write all this in most of our statements. Now, when we say electron transport chain, is a series of electron carrying compounds, and we refer them as electron acceptors or electron carriers. Now, these ones, they carry electrons and they transfer them in a series of what we refer as oxidation reduction reactions. Now, this series of oxidation reduction reactions, it involves the gain and the loss of electrons. And when these electrons move from one electron carrier to another, energy is released. And in the process, that energy that has been released, it is used to drive the synthesis of ATP. Now, that is why now we want to talk about how ATP is made, and this involves two ways. Now, before I talk of the two ways, how does this energy drive the synthesis of ATP? How is it lost? Now, when electrons are excited in this process of photosynthesis, they move from a low energy level or a low energy state to a higher energy state. Now, in that higher energy state, as they move through the electron transport chain, they lose energy because they move, it's like a staircase. They start moving from the upper section or upper area, let's say the third floor, to the first floor using staircases, and in that case energy is lost. That energy is the one that is used to drive the synthesis of ATP, because we said the synthesis of ATP is a condensation reaction and it requires an input of energy. In our first statement at the top here, we said that the synthesis reaction, that is of ATP, is provided by the enzyme ATPase, and it requires energy input. That energy input is actually obtained, that energy that is required here is actually obtained from the energy that is lost as the electrons move from one electron carrier to another through this series of reactions, which we refer as the electron transport chain. Now, ATP is made in two ways. One of the ways is the use of energy that has been released from catabolic reactions, and this is what we refer as the cellular respiration. Now, we have another way that ATP is made is by the removal of the hydrogen atoms from several of the intermediate compounds in a metabolic pathway. Now, when we talk of these intermediate compounds, we talk of reduced NADP, which we can equally refer it as NADPH without the term reduced. If you just write NADP, in that case we are referring to it to be oxidized. Once it gains hydrogen atoms, we say it to be reduced NADP, or we can just say NADPH, because this H here, it is showing that it has gained that electron. Now, when we talk of the removal of hydrogen atoms, the energy that was used to bond these hydrogen atoms to the NADP, that's the reduced NADP, that energy now is used to join the ADP and inorganic phosphate to form ATP. Now, I want us to look at the next part, which talks about the continuation of the electron transport chain. And this now we want to understand how these electron carriers are oxidized or reduced. Now, when hydrogen atoms are removed from a compound and then they are picked up by a nitrogen carrier or acceptor, then we say that it becomes that hydrogen acceptor, it becomes reduced. That's why we are saying the acceptor is reduced. Now, this one is something to remember from chemistry, where we talk about oil rig, or we can solve Leojar, meaning oxidation is loss of electrons, reduction is gain of electrons. Or we can say loss of electrons is oxidation, gain of electrons is reduction. So we talk of oil rig or Leojar. Now, if you look at the first row here, we see oxygen. When it is being gained, that is oxidation. When it is being lost, that is reduction. Now, if you look at this, you realize that these two, hydrogen and electrons, when it comes to oxidation, they both deal with the loss, which is different with oxygen, which deals with the gain from your chemistry. Now, on this part, when we talk about reduction, we have the loss of oxygen. But in this, when we talk of hydrogen and electrons, when a substance undergoes reduction, is when it gains the hydrogen, that's the hydrogen and the electrons. Now, electrons that are from the hydrogen atoms are transferred along a series of carriers, now which we refer to the electron transport chain. Now, this is now what you realized. We said that when the electrons are transferred from one electron carrier to another through the electron transport chain, energy is actually lost, and this energy is the one that is used to drive the reaction, that is to drive the synthesis of ATP, what we will learn in future as photophosphorylation. Now, I want you to understand that there are key terms that you need to understand in the electron transport chain: the gain and the loss of electrons and hydrogen atoms. And that's why I'm saying here that the component of the electron transport chain are reduced when they receive the electrons, or we can talk of hydrogen atoms, and oxidized when they transfer the electrons or they transfer the hydrogen atoms. The redox reactions in this case, which involve the loss and gain of electrons, the loss and gain of hydrogen atoms. Now, these redox reactions, they release a small amount of energy which is used to drive the synthesis of a molecule of ATP. And that brings me now to the end of that section for today's session.